And we know chemistry is all about writing equations, yeah? So here they want you to do some calculations to work out the pH. So started from the sodium oxide. So started from the sodium oxide, we need the MR of the sodium oxide. So I got 23.1 times 2 plus 16.0 times 1. This is 62.2. But that's just my periodic table. So your periodic table might just give you 62. So the mole of Na2O is 3.10 over 62.2. So that's the mass over the MR, that's the mole. And then the concentration, so what do I need? I do need this equation, balance, because if I want to work out the pH of the solution, which is essentially NaOH, I need the mole of NaOH, I need the concentration of NaOH relative to that. So from the balance equation, the mole of the NaOH relative to the Na2O is going to be 2 of the NaOH is formed from 1 of the Na2O. Now I'm going to put in the actual value that I want. So that's the mole of the Na2O. That's the actual mole that react the Na2O. On top is going to be the concentration in a square bracket, the concentration of the NaOH in mole per dm cube. So I need to convert my volume to dm cube. So I can work out my concentration of NaOH in mole per dm cube is going to be 2 times 3.10 over 62.2 times 1 over 400 times 10 to the minus 3. So that's just moving things around really. And I got that to be 0.249196, etc., etc. I don't want to run off too early, so that's why I put in a lot more significant figure than I would normally have. So we know that NaOH is a strong base, so I dissociate fully into that. So therefore, the concentration of OH minus is the concentration of NaOH, 1:1 there. So that's 0.24196 mole per dm cube. Okay, but that is the concentration of OH minus, and when we want the pH, which is to do with the H plus concentration, so there are two ways of doing it. I know some teacher would have taught you POH is minus log 10 of OH minus, and if I take the log and the negative of it, I will get 0.60346, and then you will also know that pH plus POH equal to 14. Therefore, pH equal to 14 minus 0.60346. 13.39654. This data were given to me in 3 sig fig. 3 sig fig, what is appropriate would have been 3 significant figure for the pH. I said most teachers will have taught you POH, but some teachers didn't, and this is another method you will have been used to. This relationship comes from Kw. So Kw is 10 to the power minus 14 at 298 Kelvin, is H plus and OH minus. So if you know your OH minus concentration, you can work out your H plus concentration, which is divided by 0.24196, and therefore you can work out pH is minus log 10 of H plus, and you will get the exact same answer. So this one comes from this relationship actually. So both of these methods are actually similar, except that some schools taught one way or the other because people don't know where this relationship comes from. If you take log 10 of both sides, you will get this relationship. Alright, so that's just 13.4 there. So moving on. Now you have that much SiCl form and all the soluble acidic product, which is HCl. You want the pH of the solution of 10. So we know it's HCl going to H plus and Cl minus. Alright, so we need the concentration of H plus, which is 1 to 1 to 1 there. So therefore the concentration of HCl is equal to the concentration of H plus. So we need the concentration of HCl. We know how much volume of water we have. Liquid plus water, so we know how much volume of water we have in here because this is just coming as a solid. So from the balance equation, the mole of the HCl is to the mole of the SiCl4, because this is what has reacted, is going to be 4 mole of HCl to 1 mole of SiCl4. Why do you think we need to balance equation? Because they like to ask, you know, questions involving calculation where you need balance equation, yeah? So I need the mol of SiCl4 because I'm given the mass. So to work out the mole, I need the MR of it, where's my periodic table? I got 170.1 there. So therefore, the mole of the HCl is just 4 times the mole of the SiCl4, which is 0.8505 gram divided by 170.1. Okay, that gave me 0.02 mole. All right, and from this information, I need the concentration of HCl. It's going to be the mole of HCl over the volume of HCl. So it's 0.02 mole. I have 800 cm³ of water. Convert that to dm cube. Because of the unit of concentration, you want it in mole per dm cube. You get 0.025 mole per dm cube. And then based on this information, where I know they fully dissociate, this gives you the pH of a strong acid. So therefore, the H plus concentration is the same as the concentration of HCl because of this equation, which is balanced. We should write it as such. Okay, so once you get the acid concentration, it's just pH equal to minus log 10 of H plus. And we are nice and happy, 1.602. Look at the data given. These are 4 significant figures. These are 3 significant figures. If I were you, I would be tempted to maybe 3 significant figures to be consistent with some of the data which have been given to 3. If all the data is given to 4, I would have put it to 4, but only one of the data is given to 4, so maybe I would just give it to 3, right? But definitely not 2, because that would be too little compared to the significant figure in the data given. But as with any rounding, I will not round off before I write off something to a higher precision, yeah? And revisit in A level, okay? Now, this is sodium hydroxide. It is a strong base. So this is pH of a strong base. It's fully dissociate, okay? So pH is equal to minus log 10 of H plus. So you got to find out the H plus concentration. That's 10 to the power minus 13.25. So that you put that into your calculator, you are going to get 10 to the power of 13.25 negative. You're going to get 5.62 times 10 to the power minus 14. Okay, and you know Kw, so the whole thing of the asking you Kw before is because you can use Kw equal to H plus and OH minus. Alright, so I can find the OH minus concentration by dividing Kw, which is 1.0 times 10 to the power minus 14 at 298 Kelvin. This value 1 times 10 to the minus 14 is given in the data booklet for Kw at 298 Kelvin, divided by the concentration of the H plus, so 5.62 to the power minus 14. I forgot, I make a mistake. I should probably do not round it up to 3 sig fig yet. I should probably have it to 4 sig fig just to be how do I say this? You shouldn't run up before you reach the final part of the calculation. Okay, so that's to avoid any rounding errors and stuff, yeah? So that is 0.1778. So now this is in 4 sig fig. I can leave my answer to 4 sig fig, or I can leave it to 3 sig fig. That'll be all right. I'm going to leave it to 3 sig fig, partly because the value given in the data booklet was actually like 1.0, or was it 1.00? So somewhere around 3 sig fig will be all right. But if you leave it to 4 sig fig, it's acceptable, partly because this is also 4 sig fig in the data. Okay, but what I've done is I provided alternative, so that should be all right, eh? Okay. of this term. So pH is minus log 10. Oops, I don't know what's wrong with that pencil. Minus log 10 of that thing in square bracket, minus log 10 of H plus concentration. So H plus in the square bracket refers to the concentration. Kw is called water dissociation constant, but they want the mathematical expression. They don't want the definition in words, so be very careful. Now we're looking at NaOH. So this is a strong base, and a strong base dissociates completely into the ions. So I'll have aqueous, aqueous, aqueous. So if I have 0.027 molar there, therefore the hydroxide concentration is 0.027 molar as well, right? Because it's 100% dissociation. So what I can do now is I can work out. Well, actually, what can I do? So if OH minus times H plus is equal to Kw, it's equal to 10 to the power minus 14. So H plus is equal to 10 to the power minus 14 divided by the OH concentration, which is 0.027. And if you know the H plus concentration, well, that's why they ask you for this particular expression. If you know this for the H plus concentration for this NaOH, then you can just sub it into there, and then you should be able to get the answer correctly. So 10 to the power minus 14 divided by 0.027. That's the concentration of H plus. Take a log 10 of that, and remember to put a negative in front, and I got 12.431. Then I can run it up because this is two significant figure given in the question. So I feel it appropriate to run it up to two significant figure, but not before I show it to more than two significant figure, because you never know if the examiner will penalize you for giving so little significant figure. But it should have been alright, because given the data it was two significant figure, you shouldn't get more significant figure than the data you were presented with to begin with. Alright. Now the next bit, they want you to use the value of Kw. This is from your data booklet. They want you to calculate H plus concentration in pure water under standard condition. So you know in Kw, this is your equation. The H2O water dissociate into H plus aqueous plus OH minus aqueous. So there's the equation for Kw. So Kw equal to H plus times OH minus concentration, where you do not divide by the concentration of H2O, because that concentration is so big that it remains largely constant. It's already taken into account. That's why it's called Kw. It's no longer Kc, it's Kw. Special, yeah? Okay. So as the H plus concentration equal to OH minus concentration, because 1:1, right? 1:1 in the balance equation. So Kw is equal to 1.0 times 10 to the power minus 14 from the data booklet. This is equal to H plus square, because they are equal, right? So I just concentration of the H plus square. Don't forget you need to square root. So do that on your calculator, and then you will get 1.0 times 10 to the power minus 7 mole per dm cube. Alright. Now they said the pH of pure water at 50 degrees Celsius is this. So it's just below 7. If you take the log of this, there's a 25 degrees Celsius under standard conditions. Okay, 298 Kelvin. Minus log 10 of this is going to give you pH 7. The pH of water, pure water, under standard condition. But this is not standard condition. It's below 6.64. They want you to calculate Kw. Alright? So if you have pure water at 298 Kelvin, it has equal concentration of H plus and OH minus, right? That's why they balance out, they get neutralized. That's why we call them neutral, because the concentration of H plus balance out the amount of OH minus, yeah? When you just boil them, in fact before boiling, you just heat them up, their pH change. But is it actually acidic? No, because it's still water. So this hasn't evaporated, this is still in the solution. So you still have equal number of H plus and OH minus. So that means this relationship there still applies. Therefore, what I can do is, actually they give me the pH, right? So I can work out the concentration first. So pH is minus log 10 of H plus. So H plus is 10 to the power minus 6.64. Okay. But then I also mentioned just now, the H plus concentration is still balanced out by the OH minus concentration because we are not taking anything out, we are just warming them up. We are not adding anything either, yeah? So Kw equal to H plus square because H plus concentration are OH minus, but they are equal, so it's just H plus square there. So the Kw at 50 degrees Celsius is equal to 10 to the power minus 6.64 square. So you are supposed to work it out one by one, but I can't be bothered, so you can work it out. And then you're going to get 5.248 times 10 to the power minus 14. You're going to get 5.25 times 10 to the power minus 14. That will be mole square dm minus 6. When you do that, that is mole per dm cube square. The unit is also given for free in the data booklet. When you get the value there, it's actually given the data booklet as that, okay? So it's 5.25 times 10 to the power minus 14. I know they just want the numerical value. It does not hurt you at all to always be sensible and write down the correct units, okay? Why does the concentration of H plus change at different temperature? Because this is an equilibrium. This is dissociation of water. Going forward is dissociating water. You are not forming anything, you are just dissociating the H2O, okay? So this is going to be endo. Because it's an equilibrium, you are governed by Le Chatelier principle. As temperature change, the equilibrium is going to absorb more heat at higher temperature. It's going to dissociate more, okay? That means you will have more H plus, you also have more OH minus, okay? But because the concentration of H plus increase, so that's why in your pH, it's going to be slightly below 7. But you still have equal number of H plus and OH minus. So drinking pure water at 50 degrees Celsius, even though the pH is that, but it is still neutral. I just want to make it clear because when I say neutral, I mean there is equal number of H plus and OH minus, okay? Okay, next bit, Kw. So Kw, the expression is actually for water. Dissociating into H plus aqueous plus OH minus aqueous. So Kw takes into account that this concentration remain unchanged because it's so big that it's already taken into account in a new constant. So this is not Kc, it's Kw. Therefore, we do not put in the concentration of water because that already takes into account the concentration of water being unchanged in the Kc, which then become Kw. Alright. So Kw increases with increasing temperature. You should know the enthalpy of this reaction is greater than 0. You are dissociating water. You are not forming any bonds at all. You are just dissociating water. It requires energy. Alright? So because you just increase the temperature of water, okay, so the ratio of H plus and OH minus is still going to be the same. Basically, you're not adding anything, you're not removing anything, you're not doing any reaction. So the amount of H plus and the OH minus in the equilibrium is still equal. However, because the forward reaction is endothermic, when you increase temperature, it's gonna favor the forward reaction, okay, to try and absorb more heat, because you want to do the opposite. You want to decrease the temperature, right? So it will absorb more heat. It will dissociate into more H plus and OH minus. Because now you dissociate into more H plus, but also more OH minus. Your pH is due to minus log 10 of H plus because you dissociate into more of this and also this. But because there is more of this, all right, so you're going to have the pH decrease slightly, okay? So at 25 degrees Celsius, your pH is equal to 7. That's because your concentration of H plus is 10 to the power minus 7. At a higher temperature, your H plus is going to be greater than 10 to the power minus 7. Therefore, your pH is going to drop below 7. You can check it with your calculator, but I'm just giving you the qualitative trend based on the Le Chatelier principle, which you already learned in O level. So Kw is a standard case study, but here this is special. This is D2O. So we're looking at D plus and OD minus. Alright, so D plus and OD minus. not H plus and OH minus because it's of D2O. All right. So calculate the pH of pure neutral D2O. All right. Assume the concentration is equivalent to that. All right. This means D plus concentration equal to OD minus concentration. Therefore, Kw, which is equal to 1.35 times 10 to the power minus 15, given in the question there, is equal to D plus square. So D plus is equal to the square root. So you're doing calculations, so you don't want to run off too early. So I gave it to a higher number of significant figure there. And then they're saying it's almost similar as H plus. So we know pH equal to minus log 10 of H plus. In this case, instead of having H plus, we have D plus. So what I do is I just substitute this value in there. So take the log 10 and then apply a negative. And what you will get is, I get 7.4348. They don't tell me what is significant figure I should put down, but I should be appropriate. This value that I'm using is 1, 2, 3 significant figure. I can and I should run it up to 3 significant figure, but not without showing the one with higher number of precision.